Okay, so we are in section 4.3 class, and we talked about 4.3 in our last class about bases. Okay, so again, what does it mean to have a basis? What's the definition of a basis for a subspace? Two very important properties. One is if you have a set of vectors and the set of vectors are linearly independent, and the set of vectors, the span of those set of vectors, the span of those set of vectors equals the space H, then you have a basis for your subspace H. Now, in a sense, the basis is considered the most efficient set of vectors that you need for the space. Okay, because like if you recall here, all right, so if you're looking for a basis for R3, is this a basis for R3? Okay, this is the E1, E2 vectors. Is that a basis for R3? And I appreciate all answers. Yasin thinks yes. Let me ask you this. Does R3, okay, Belen's asking, okay, Belen's asking, so we're looking at 4.3 here. Does R3 equal the span of these two vectors, E1 and E2? If you were to take any linear combination of 1, 0, 0 and 0, 1, 0, could that equal all vectors in three-dimensional space? So in other words, that's right, Nikhil. Definitely not. Definitely not. Now let's see why. R cubed is not the span of those two vectors, and so you don't have a basis. So like for instance, let's say that you had the vector 3, 4, and 5. 3, 4, and 5 could never equal a linear combination of E1 and E2. There's no way you would ever get this vector 3, 4, 5, which is an R3, because the two bottom numbers here are zeros. So you see there are vectors in three-dimensional space that are that span of the E1 and E2 vectors, it doesn't reach them. You see, the E1 and E2 vectors, any span of those two vectors would only reach points in basically the XY plane. It's not going to reach points above or below the XY plane. Yasin, does that make good sense? Okay, excellent, excellent. All right, are there any questions on that before I do another quick example? I always think of examples to help me understand definitions. All right, let's try another one. Let's try another one here. Okay. Let's stick with three-dimensional space. Is this set of four vectors a basis for R3? Well, let me ask you. I'll call the vectors, this is E1, E2, E3, and I'll call that just V. Does the span of E1, E2, E3, and V, is it equal to three-dimensional space? Good. It is. It absolutely is. If you were to take a linear combination of E1, E2, and E3, and then just put a 0 before that fourth vector V, that would equal any vector in R3 could be reached. For instance, if you had 3, 4, 5, for example, 3, 4, 5, 3, 4, 5. Well, what would C1 need to be? C1 would be 3, right, Bellin? C2 would be 4, good. And C3 would be 5, good, good. So any vector in three-dimensional space is in the span of this set of vectors, these four vectors. So yes, this is true. But now we have to ask a second question. Is the set of vectors E1, E2, E3, and V, is it linearly independent? Okay. Well, let's think about this. If the set of vectors were linearly independent, that means that, well, let's think about it like this. If the set of vectors were linearly dependent, that means one of the vectors can be written as a linear combination of the other vectors. Okay, one of the vectors can be written as a linear combination of the other vectors. So let's take the vector V, which is 1, 2, 3. Can that be expressed as a linear combination of the first three vectors? So is V equal to something times E1 plus something times E2 plus something times E3? Are there, numbers? Okay, what are the numbers? The vector V equals, what are the numbers in front of E1, E2, E3? Okay, Belen, 1 times E1 plus, wouldn't be 0 times E2. Right, Marcella, 2 times E2. And I appreciate all responses. Thank you. Very good. And then what would be in front of E3? A 3. So is the set of vectors linearly independent? Does this relationship here, the fact that V can be written as a linear combination of the other 3 vectors, is that an independent relationship or a dependent relationship? Dependent. That's right, Marcella. So the answer is no, those vectors aren't linearly independent, and so we do not have a basis for R3. We do not have a basis here. Are there any questions on that? Okay. So you notice we have 4 vectors in 3-dimensional space. Can we have a linearly independent set if we have more vectors than the dimension of the space? Do you think that's possible? I mean, put it this way. For a basis, do the first 3 vectors, E1, E2, and E3, is that enough to do the job, to give us a basis for R3? Do E1, E2, and E3, does that set of vectors form a basis for R3? Can any, they're clearly linearly independent. And can any vector in 3-dimensional space be written as a linear combination of E1, E2, and E3, or I, J, and K? That's right. David, I'm glad you're with us. Don't go anywhere, okay? Don't go anywhere. I've been calling your name, but I'm glad you're here now. So I have to talk about the exam, so hang around, okay? Thank you. Thank you. Glad you're here. So yeah, so essentially we have too many vectors. A basis for 3-dimensional space, a basis for 3-dimensional space, these 3 vectors are all you need. If you have any less, you won't have a basis. If you have any more, you won't have a basis for R3. Okay, so is this helpful, this little discussion on bases? Is this giving you a good feel for what's going on here? Excellent, excellent. Okay, thank you, Marcella. What I want to do one example here, and let me do that example before, well, let me just do it here. Let me bring it up. Okay, take a moment to copy the example down. Excellent. Jonathan and Zishan, are you here? Jonathan, are you with us? Can you hear me? Okay, all right, let me let you copy the example down. Incidentally, we talked last time about finding a basis for the column space of a matrix. Here, we're going to find a basis for the null space of the matrix. Okay, so to find the null space of a matrix, of course, we're going to solve the system A times X equals the zero vector. Now, what are the dimensions of A? What's the size of matrix A? I should probably call it size. What's the size of matrix A? How many rows, how many columns? That's right, Yasin. It's a 3 by 5. Good. And Belen, yes. Thank you, everybody. So the vector X here is going to be in the null space because A is mapping the X vector to the zero vector. The null space is a subset of what? R what? The null space is a subset of R. What's the dimension? 3, R3, R4. Is it 3-dimensional space, 4-dimensional space, 5-dimensional space? The null space is a subset of the what subspace of what space? Well, think about what's going on between A and X. What operation is going on between A and X? You are taking A and you are blanking it by X. What are we doing? Is this a matrix product on the left side here? Is this the product of two matrices? Yes or no? Do you agree we're taking the matrix A, we're multiplying the matrix A, we're multiplying the vector X by the matrix A? Give me a thumbs up if you agree with that. Absolutely. So if we're doing a multiplication of two matrices, excellent, then, well, matrix multiplication has to be defined. X is a vector. X is a vector. So the number of columns is going to be 1. But the number of rows is going to be 5. Right? That's right, Belen. That's right, Yasin. It has to be, or else you wouldn't be able to multiply. You wouldn't be able to multiply those two matrices. A vector is a matrix. The zero vector, by the way, what would the dimensions be of the zero vector? How many rows are the size of the zero vector? It would be a 3 by 1. A 3 by 1. Because you look then to the outside numbers for that. Okay, so the null space then is a subspace of R what? It's a subspace of R5. That's right. Good, Belen. Because the vector X here is a 5 by 1 vector. It lives in 5-dimensional space. So what we want to do is we want to find a basis for this null space. So let's go ahead and do that. Okay, so I don't want you to forget how to do row operations. Okay, so I'm working it out here with the row operations. So remember when you're, and students tend to make this mistake, you are solving this augmented matrix. Okay, but sometimes what happens is students don't put the column of zeros on the right side, and that's wrong. When you're solving for the null space, you're solving the matrix equation A times X equals a zero vector. Okay, now what I'm going to do is I'm going to, first of all, I'm going to do 2 row interchanges here because I want the 1 here. I want the 1 to be my pivot because I'm a human being and I like 1 as my pivot. And then I'm going to have the 2 next, below the 1. I just choose to do that. And that's going to give me this matrix, this augmented matrix. Okay, so we have here where the 2 is and the -3 is, we want zeros there. So we're going to use the 1 as a pivot. So we'll take -2 times the first row, add it to the second row, replace the second row by that result. And then we'll take 3 times the first row, add it to the third row, replace the third row with that result. It's important that we keep our row operations fresh in our mind and we know how to do them. We don't want to be using MATLAB to do all of our row operations, right? Because the theory won't be clear to us that we've learned. Okay, so now what we have here is I have a pivot that I like here at 1, and I'm going to use it to reduce, to get this a 5, the 0 where the 5 is. So we'll take -5 times row 2, add to the third row, replace the third row by that result. To get it in reduced echelon form, okay, here I have a leading entry here, zeros are in the rest of the column, and I have a leading entry of 1 here, so I want a 0 where the 2 is. Okay, so I'm going to use that 1 as a pivot, multiply the second row by -2, add it to the first row, replace the first row by that result. And that's as good as it's going to get. We get it in reduced echelon form. All right, so in this augmented matrix, how many meaningful equations are there? How many meaningful equations are there? 2. That's right, Mikhail. How many variables are there? 5. That's right. So therefore, we have 3 variables. And what I like to do is I like to take the augmented matrix and now write it as a system of equations, and then we can figure out what the 3 variables are. Are there any questions before I move to the next page? Okay. We go to the next page. Okay, so now here's our system of equations. Okay, based on the bottom equation, you're going to let x4 and x5 be free variables. So x3 then is -2x4 plus 2x5. And then based on the first equation, the only variables you haven't accounted for are x1 and x2. Well, let x2 be free. And then x1 is 2x2 plus x4 minus 3x5. Okay. So we're going to write the vector x in parametric vector form. And I would want to see this kind of work on your next exam. I mean, this is no big deal to do the row operations and write this out. This is no big deal. Okay, and you see now that we have this, we've written out our variables, and we have two basic variables, x1 and x3, in terms of the free variables, and now we can expand that solution out in parametric vector form. Notice that, and I'm calling these vectors u, v, and w. Okay, I'm calling these vectors u, v, and w, and they form the spanning set for the null space. That set of vectors is linearly independent and spans the null space. So your basis here, okay, your basis for the null space the basis for the null space of A is going to be those three vectors. Those three vectors generate the null space of A. And notice those three vectors, u, v, and w, all live in five-dimensional space. Truly a fascinating topic, section 4.3, and very important for us. That's right, Mikhail. And you know, I'm not going to be asking you to always, I mean, it's sort of like if you've already done row operations, it can be repetitive to have to continue to redo them all the time, but we shouldn't forget how to do them. And finding the basis for a null space is something where, we ought to do our row operations for that. Because then C2, you get it in parametric vector form. It's just something you want to do, You don't want to read off what MATLAB gives you, and you lose your ability to, or you lose the sort of the connection to you lose clarity. That's the word I'm looking for. You lose clarity when you use technology to do your work all the time for you. You lose clarity in understanding the math. And that clarity is very important. You definitely need it, right, for like true-false questions, right? And conceptual questions, you need it. Okay, are there any questions on this? Mikhail says, yes, it makes sense. It's hold on. Well, yeah, my feeling, Mikhail, is I believe I like to do everything by hand, and then I can verify it with the computer. But you understand what I mean, how it's valuable to do things by hand. I mean, it just makes the material more clear and intuitive, and that's very important for this course. Excellent. Are there any questions before I stop the recording? Okay. Okay, then I will stop the recording. Very good.